An ancient impact splashed evidence of the Moon's early mantle makeup onto its surface. Now researchers are piecing together models, maps, and samples to bring these mysteries to light. Despite our long history with Earth's closest celestial neighbor, much remains unknown about the Moon, including about asymmetries between its nearside and farside, for example, in crustal thickness and evidence of volcanic activity. Now Moriarty et al. Combine models, remote sensing data, and insights from lunar samples to refine the timeline of the Moon's development, focusing on a feature called the South Pole-Aitken Basin, SPA. This basin, the oldest, deepest, and largest on the Moon, was formed by a massive impact early in lunar history, roughly 4.3 billion years ago, and its shape and composition can give researchers an idea of what the Moon was like at that moment in time. Model simulations show that the impact that made the SPA was energetic enough to eject materials from the Moon's early mantle. The simulated splash pattern corresponds to areas of the lunar surface known to be rich in thorium, and the researchers propose that this ejected material represents the dregs of an early molten mantle. As the Moon's early magma ocean cooled, minerals and elements crystallized, and either rose to become part of the crust or sank to become part of the lower mantle. Late in this process, thorium and other dense, incompatible elements were left in dregs sandwiched between the crust and mantle. To explain the dramatic differences between the lunar nearside and farside, earlier theories suggested that thorium-rich dregs occurred only on the nearside. However, the new results demonstrate that these substances were ejected by an impact on the Moon's farside. This observation implies that at the time of the impact, thorium-rich material must have been globally distributed and had not yet migrated to the nearside or sunk toward the core, which is expected to occur at the end of the mantle crystallization process because of its high density. Unlike the ejected materials, the rock melted by the Pole-Aitken does not contain abundant thorium. Because an impact can melt materials from depths greater than those where ejected material originates, the thorium shortage in the melt indicates that the early mantle had distinct layers, a thorium-rich layer just under the crust, and a different layer beneath that. The scientists identified potential targets for future sample missions, focusing on ejected material, which would yield a clearer picture of the Moon's early mantle. Further work should also focus on pinpointing the SPA's age. They say because the vast ancient basin is key to understanding the timeline of lunar history. Geophysical data has suggested that the base of the Moon mantle is partially molten or contains ilmenite, but an improved rheology model puts the existence of this layer in doubt. The structure of a planet's deep interior can only be constrained directly using chemical tracers and limited geophysical information. The lowermost mantle is a particularly intriguing region of the Moon's interior, as it contains clues to the early evolution of our satellite. The lowermost 150 kilometers of the mantle has been described as weak, based on low seismic velocity and the way it dissipates tiny energy. Previous studies have proposed that this weak layer contains melts. However, it is hard to explain how the Moon's mantle can be hot enough to melt, unless it contains significant amounts of water. Alternatively, this layer may be enriched in the mineral ilmenite. Either interpretation has important implications for the formation and early evolution of the Moon. However, Walter Rover et al. 2023 suggests that there may be no such partially molten layer at the base of the lunar mantle after all. One constraint on the deep interior of the Moon comes from precise measurements of the shape and motion of the Moon, especially tides. Surprisingly, the lunar interior dissipates tidal energy more efficiently in periods of 1 month than 1 year. Classical viscoelastic models of the lunar interior can explain this observation only if there is a distinct layer at the base of the mantle. However, these models may not be the best description of the complex behavior of lunar rocks. Walter Rover et al. 2023 showed that a dissipation model in Sunberg and Cooper 2010 developed can explain the higher dissipation at 1 month period without requiring a separate separate deep mantle layer. If this arguably more realistic mechanical model adequately represents the interior of the Moon, the lunar mantle could be made of a single material and be solid for life. At this point, though, both the uniform and the layered model remain admissible, given the limited data available. This situation can only be remedied by collecting new geophysical data, especially on the far side of the Moon. Several teams have proposed missions to the Moon with geophysical focus. These missions, as well as improvements in satellite tracking technologies, would be crucial for better understanding the interior structure and early history of our natural satellite. As we stand on the cusp of a new era in lunar exploration, the mysteries of the Moon, as ancient heart, beckon us with an irresistible pull, a cosmic whisper from billions of years ago that demands our attention. Imagine the thrill. Humanity's quest to unravel the South Pole-Aitken Basin, SPA, isn't just science. It's a profound journey into the origins of our solar system, where each discovery ignites the soul and reshapes our understanding of planetary birth. Recent breakthroughs from China's Change 6 mission, which triumphantly returned the first samples from the Moon's farside in June 2024, have electrified the scientific community. These precious rocks, scooped from the SPS Apollo crater, pinpoint the basin's cataclysmic formation to approximately 4.25 billion years ago, aligning with models of an oblique, high-energy impact that excavated deep into the mantle. Analyzers reveal an ultra-depleted mantle source beneath the basin, poorer in incompatible elements than previously thought, suggesting a heterogeneous early magma ocean that fractionated unevenly. Even more intriguingly, the samples indicate a more reduced mantle environment low oxygen, fugacity hinting at volatile influences or cornerstone interaction that could explain the stark nearside farside divide in volcanism and crustal composition. This isn't mere data. It's a vivid portrait of a young moon, born by tectonic forces, where thorium-rich dregs were flung across the surface, challenging earlier theories of localized mantle overturn. Yet, the debate over the lunar mantle's deepest secrets rages on. Walter Rova et al. As 2023 rheology model, emphasizing andrade viscoelasticity, cast doubt on a partially molten basal layer, proposing instead a uniform, solid mantle that dissipates tidal energy through grain boundary sliding. Recent tidal love number measurements from Grail data reinforce this, suggesting a low viscosity zone without melts, but only if we refine our mechanical assumptions. As a space researcher who spent nights poring over seismic whispers and gravitational maps, I feel the urgency. These findings stir the imagination, but ambiguities persist, fueling our passion to probe further. Enter the vanguard of future missions. NASA's Artemis program, with its 2026 moon landing near the South Pole, promises insight in geophysical stations to map farside quakes and heat flow, directly testing mantle models. Firefly Aerospace's Blue Ghost, which touched down in early 2025, is already beaming back data on farside regolith, while proposals for SPA-specific rovers aim to sample those elusive ejected mantle fragments. Picture it. Astronauts or robots sifting through thorium-laced soils, unlocking timelines of crystallization and migration, echo Earth's own infancy. This isn't abstract academia, it's humanity's shared heritage, a lunar legacy that binds us to the stars. The South Basin, that colossal star on the Moon's hidden face, holds the blueprint for unfolding chaos and evolution. By pursuing these clues with unyielding resolve, we don't just advance knowledge. We honor the wonder that first drew our gaze skyward, inspiring generations to dream bigger. The Moon awaits. Let's seize its secrets and illuminate the cosmos. Don't forget to hit like to support